Hello, my name is Boshen Zhang, and I'm glad to introduce our paper titled Learning from Noisy Labels with Coarse-to-Fine Sample Credibility Modeling. In this work, we propose a effective learning from noisy label methods called Crema, which is the shorts for coarse-to-fine sample credibility modeling and adaptive loss reweighting, which performs well on both synthetic and real-world noisy label scenarios. Okay, first, some backgrounds. Deep neural networks are known to be data hungry. A large part of its success can be attributed to large-scale, well-annotated datasets. However, in most cases, acquiring such a large-scale dataset is expensive. Instead, there are alternative ways such as verbally labeling, crowdsourcing, or using model predictions as pseudo-labels. However, these methods inevitably yield noisy labels, and unfortunately, directly training deep neural networks with corrupted labels can do harm to the generalization performance. Towards these problems, previous learning from noisy labels methods are proposed. The first one is sample correction, which trying to identify and drop the noisy samples during training. However, it is difficult to separate the noisy samples perfectly. The second one is called label corrections, which trying to correct the labels of all training samples. However, this method suffers from correction error. So our method is motivated by empirical observations that we find clean and noisy samples manifest distinctive statistical properties during training. Specifically, clean samples yield relatively smaller loss value and more consistent predictions. We also find that the full data cannot be perfectly separated by using a simple statistical metrics such as mean and standard deviations of loss value, which means hard noisy samples always exists, which still pose challenges to LNL algorithms. Based on this, we propose Crema, which is a coarse-to-fine sample credibility modeling strategies. Easy and hard noisy samples are handled respectively in spirit of divide and conquer. Thirdly, likelihood estimation of historical credibility sequence is proposed to distinguish hard noisy samples. Okay, firstly, the coarse-level sample selection is based on the well-known small loss criterion, which identify a sample as clean when the loss value is smaller than a predefined threshold. So for easily categorized noisy samples, we propose a selective label update strategies, which means we only update the labels of the coarsely separated noisy ones. We empirically find that compared with the previous global label correction counterpart, the proposed method is more effective to mitigate the problem of correction error. Secondly, for the hard noisy samples, which hybrid with clean ones, we propose a fine-grained sequential credibility modeling method. Compared with previous sample credibility modeling method, which measure the label quality by a simple point of time, in Crema, we propose to leverage the temporal information with two terms. The first one is a stability measurement term, and the second one is a log likelihood term. With the consideration of loss value and temporal information, the credibility of each sample is modeled and used to guide the learning procedure by a sample reweighting scheme. So putting this all together, this is a workflow of Crema. The first step is coarse-level separation. Second step is fine-grained sequential credibility modeling step. The third one is a selective label update scheme. The proposed Crema is verified on synthetic and real-world noisy datasets. Firstly, three types of synthetic label noise are considered: symmetric, asymmetric, and pair flip. One text, IMDB, and three visual datasets, MNIST, CIFAR 10, and CIFAR 100 are tested. And the results show that Crema achieved the best performance against other LNL methods. Same results can also be found in real-world noisy datasets, Animal 10 and Closing 1 million, which demonstrated the effectiveness of Crema. We also carefully conduct experiments to verify the effectiveness of each key component within Crema and investigate the sensitivity to the hyperparameters within Crema. Finally, we visualize the learned sample credibility weight between Crema and the previous sample credibility modeling method. The results show that Crema is more effective to identify noise and clean samples. That is all. Thanks for your attention.